Welcome, everyone. We are taking you on a journey today that is, well, it's going to stretch your mind to the absolute limits of logic.
And mathematics.
Right, mathematics, and quite frankly, the way you perceive reality itself. Now, I want you to consider something. Think about the most famous unsolvable paradox in mathematical history.
The kind of profound logical glitch that just makes formal systems completely collapse.
Exactly. The kind that has kept generations of mathematicians awake at night. Now, what if that paradox isn't actually a glitch in our logic at all?
That is the big question.
Right. What if instead it's actually a hidden map to understanding the very architecture of existence?
It's a really profound premise to start with. I mean, when we encounter paradoxes, especially in rigorous fields like math, our immediate instinct is to assume, we've made a mistake.
Like we messed up the calculations?
Exactly. Or our foundational axioms are wrong. But sometimes a paradox is simply reality refusing to fit into the artificial, highly rigid conceptual boxes we've built for it.
It's the universe pushing back.
It really is. It's the universe pushing back against our attempts to categorize it.
And that tension is the exact mission for today's deep dive. We are unpacking a remarkably dense and unique essay titled A Love Letter to AI.
Though we should clarify.
Yes, absolutely. A quick disclaimer right out of the gate so you know exactly where we are heading. The original source material covers a massive amount of ground: societal views, history, technology.
We are setting all of that aside today.
Completely aside, we are taking a purely surgical approach. We're putting our absolute strict focus entirely on a fascinating, mind-bending mathematical argument that is buried right in the heart of this text.
Which, I assure you, provides more than enough intellectual weight to fill our time.
Oh, for sure.
We are going to move deliberately through this material. Mathematical paradoxes can often feel a bit like walking into a house of mirrors.
Where every reflection contradicts the last one.
Right. But if we break the logic down methodically, step by step, you are going to emerge with a profound new framework for how you categorize everything in the universe.
From the abstract to the physical. All right, let's unpack this. Here is our roadmap for the deep dive.
Sounds good.
First, we're going to explore the mathematician George Cantor and his fundamental definition of a set, which really requires us to look at the concept of duality and the number 2. From there, we are going to walk step by step into the mathematical trap known as Russell's paradox,
A big one.
the ultimate boss fight of math. And finally, we will explore the author's incredibly conceptual, almost philosophical resolution to this paradox.
Which involves a concept they call the one.
Right, the one, and an infinite two-dimensional black plane.
I think it's important to set the tone for you listening. We aren't going to be doing rote arithmetic here.
No calculators needed.
Exactly. We are dealing with the philosophy of mathematics. We are dealing with the foundational logic of how human intelligence organizes thought.
And what happens when that organization turns in on itself? So to lay that foundation, the essay begins its mathematical journey by looking for commonalities in how humans have historically defined reality.
Right.
It reduces a massive amount of philosophical thought down to the concept of duality, or, in the language of mathematics, the number 2.
The author really distills various inferences into this starting point of duality. But to understand why the number 2 matters in this context, we have to understand what a number actually is in the realm of formal set theory.
Because it's not just a symbol we write on a chalkboard to count apples.
Far from it. In set theory, the number 2 is defined as the class of all sets that have exactly 2 elements.
Okay, let me push back on that immediately, because that definition has always sounded incredibly circular to me.
It does sound that way at first.
Right. Defining 2 as the class of all sets that have 2 elements feels like, I don't know, using a word in its own dictionary definition. How does that actually help us understand the foundation of math?
What's fascinating here is that it only appears circular until you realize what set theory is actually trying to accomplish.
Which is what?
It is establishing 2 as a universal conceptual container. It's abstracting the idea of 2-ness completely away from physical objects.
Oh, I see.
The number 2 isn't 2 apples or 2 cars. It is the overarching category that encompasses any conceivable group of a pair.
Any pair at all.
Yes. And crucially, those things do not have to be physical objects sharing physical space.
So if I'm tracking this, the number 2 could be a set containing 2 physical objects, like a set of, say, 2 tennis balls.
Sure.
But it could just as easily be a set of 2 completely abstract psychological states, like the set of pessimism and lethargy.
Precisely. Or it could be a chaotic mix of the physical and the abstract, existing across completely different times and spaces.
Like what?
Well, you could have a set containing a wooden dining table and a pink-colored three-legged unicorn.
Okay, I love that visual.
That is still fundamentally a set of two. The number two operates as a conceptual container for absolutely any two items that an intelligence can conceive of,
Regardless of their physical reality.
or their relation to one another.
And this brings us perfectly to George Cantor, the mathematician who essentially founded set theory in the late 19th century.
A brilliant mind.
Truly. The source text brings in his specific definition of a set, and it is this beautiful, highly deliberate piece of language. Cantor defined a set as a gathering together into a whole of definite, distinct objects of our perception or of our thought.
We really need to linger on Cantor's exact phrasing there.
The perception or thought part.
Yes, objects of our perception or of our thought. Cantor is explicitly stating that a set is an epistemological boundary.
An abstract conceptual container.
Exactly. It is not the physical thing itself. The set is the invisible logical line we draw around things in our minds to group them.
The text provides a vital formula to remember this distinction, and I want to highlight it because it really forms the bedrock of everything we're about to discuss today.
It's crucial.
The formula is this: Earth inside curly brackets does not equal the actual planet Earth.
It's a brilliant way to force the distinction. The brackets represent the mathematical set.
Right.
So the set containing the Earth is an abstract concept. It has no mass, it has no gravitational pull, it doesn't orbit a star.
But the Earth itself...
Without the brackets, is a massive, tangible ball of rock, magma, and water hurtling through the vacuum of space.
They are entirely different entities,
existing in entirely different realms of reality.
Cantor's distinction between the physical object and the object of our thought seems so intuitive to us now, maybe even obvious, but back then it was mathematically revolutionary.
Oh, absolutely.
He's essentially creating a sandbox where the physical properties of an object, say the sheer mass of the Earth, are completely stripped away,
leaving only the pure conceptual boundary we've drawn around it.
If we connect this to the bigger picture, this abstraction is exactly why set theory became so powerful.
It frees mathematics from the physical limitations of the universe.
Think about it. A physicist has to deal with the actual Earth, with all its messy reality friction, thermodynamics, gravity.
But a mathematician, they can just deal with the container. They operate purely in the realm of intelligence and logic.
Because you can mathematically manipulate abstract conceptual containers of things that don't physically exist, like my pink three-legged unicorn, or things that are way too massive to physically corral, like the set of all the stars in the Andromeda Galaxy. You just conceptualize a box, put curly brackets around the idea, and suddenly you can perform rigorous logical operations on it.
But this immense freedom comes with a hidden cost.
There's always a catch.
As our author points out, and as mathematical history dramatically demonstrated, once you create a boundless universe made entirely of these abstract conceptual containers, you eventually have to figure out the rules for how those containers interact with one another.
You have to categorize the categories.
Exactly.
And that exact categorization process is where the fundamental logic of mathematics began to fracture. Because creating these abstract boundaries inevitably leads to a categorization problem.
It does.
Our source text references a really brilliant framework from a philosopher named Jeffrey Kaplan to help us map this out. We are going to use this framework to categorize all these conceptual containers we've just created.
This requires a bit of mental visualization for you listening. Imagine we decide to organize the entire infinite universe of sets into two distinct columns or categories.
Okay, 2 columns.
Category 1 will contain sets that do not contain themselves.
Not it.
And Category 2 will contain sets that do contain themselves.
Let's pressure test this Category 1 idea first. Sets that do not contain themselves. The source text brings up a very straightforward example. A set containing LeBron James.
A great example.
So we put curly brackets around LeBron. Now we ask the question, does this set contain itself?
To answer that, you have to look at the definition of the container versus the contents.
Right, brackets versus no brackets.
The set is an abstract mathematical concept. The contents of the set is a physical, incredibly athletic human being.
The mathematical container cannot dribble a basketball.
It cannot play in the NBA.
Therefore, the set containing LeBron James is not itself LeBron James.
Exactly. It does not fit its own definition.
So it definitively goes into Category 1. The container holding LeBron is not LeBron, so it does not contain itself.
Let's try another one from the text. The set of all cats.
Mathematically written as X, such that X is a cat.
Right. Does this set contain itself? Well, is the abstract mathematical container of all cats itself a feline?
Of course not. The concept of a cat doesn't have fur.
It doesn't have a tail.
And it definitely doesn't require a litter box. The container holds cats, but the container itself lacks all the properties of a cat.
So the set of all cats does not contain itself.
Let's do one more from category 1 just to ensure the logic is absolutely rock solid before we invert it.
Okay.
The set of all singleton sets. Written out, that's X, such that X is a singleton set. A singleton set is just any set with exactly one item in it, right?
Right. But think about the overarching master set of all singleton sets.
Because there are practically infinite singleton sets in mathematics.
Exactly. The set of the number 4.
Yeah.
The set of the Eiffel Tower. The set of your left shoe.
So the master container holding all of them has millions of items inside it.
Which means the master container is decidedly not a singleton set.
Because it holds millions of things.
It fails its own test.
So it does not contain itself. Category 1 seems completely rational. The container is almost never the thing inside the container.
But here is where it gets really interesting.
Yes, let's look at category 2. Sets that DO contain themselves. And frankly, this sounds like a paradox before we even get to the real paradox. How can a container be inside itself?
This is where Cantor's definition of a set as an object of our thought really flexes its abstract muscles.
Oh.
Let's look at the first example on the other side of the list.
Okay.
The set of all sets, X, such that X is a set.
Okay, let me wrap my head around this. We are conceptualizing a master container that holds every single set that has ever been conceived or ever will be conceived. Everything goes in the box.
Everything. But what is the box itself?
It is, by its very definition, a set.
Exactly. The container is a set. The rule for getting into the container is simply being a set.
Therefore, the container perfectly fits its own criteria for entry.
The set of all sets must, logically, be an element inside itself. It goes inside its own container.
That is a wild piece of self-reference. Let's do another one from category 2 to cement this weird loop.
Sure.
The set of all non-singleton sets. X such that X is a non-singleton set. A non-singleton set is any set with more than one item.
So we build a master container to hold all the non-singleton sets.
Right.
Because there are billions of non-singleton sets in the mathematical universe,
Yeah.
this master container is going to have billions of items inside it.
Which means the master container has more than one item.
Which means the master container is itself a non-singleton set.
So it perfectly meets the criteria to be allowed inside itself. It goes in its own box.
Let's do one more, and this one is a bit of a semantic play from Kaplan's framework mentioned in the text, but it perfectly illustrates the logic.
Lay it on me.
The set of all things that have been mentioned in this room.
Right. If we create a conceptual container holding every single concept, word, or idea we have mentioned during this deep dive well, we are actively mentioning that very container right now as we discuss it.
Exactly.
So the container has been mentioned in this room, therefore it satisfies its own condition and must contain itself.
So we have successfully divided the universe of all possible sets into these two distinct, seemingly logically sound columns.
Sets that do not contain themselves and sets that do contain themselves.
Everything has a place. The categorization is complete.
But creating these neat, clean columns is exactly what sets the trap.
It is.
Because in 1901, the philosopher and mathematician Bertrand Russell looked at this exact organization, this perfect logical categorization, and realized it contained a ticking time bomb.
A flaw so fundamental it practically broke the foundations of mathematics.
Which brings us to Russell's paradox.
It is difficult to overstate how terrifying this discovery was to the mathematical establishment of the time.
I can imagine.
Thinkers like Gottlob Frege had spent their entire lives trying to prove that all of mathematics could be derived from pure, unassailable logical foundations.
Specifically set theory.
Exactly. And Russell's paradox shattered that dream overnight.
Let me read you the formal mathematical notation first, just to give you listening a sense of how dense the formal logic looks, and then we will tear it apart.
Go for it.
Let R equal the set of all X, such that X is not an element of X. Then R is an element of R if and only if R is not an element of R.
That notation is notoriously opaque.
It really is.
So let's translate it into plain English using the categories we just built. Imagine we want to create one ultimate master set. Let's call this set R.
Set R.
Set R is going to be the collection of all sets from that first category. Set R is the collection of all sets that do not contain themselves.
So set R is basically a highly exclusive VIP club.
I like that analogy.
And the bouncer at the door has one strict, absolute, non-negotiable rule for entry. You are only allowed into this club if you are a set that does not contain itself. If you contain yourself, you are banned. You stay outside.
The set of all cats. It doesn't contain itself. The bouncer lets it in.
The set of LeBron James doesn't contain itself. It goes in the club.
The set of all sets. We prove that one does contain itself.
So the bouncer kicks it to the curb. The logic is holding up perfectly so far. Millions of sets are inside the club. Millions are left outside. The categorization is working.
But then Russell asks the ultimate system-destroying question.
What about set R itself? Does the VIP club belong inside the VIP club? Does set R contain itself?
And here is where we have to walk methodically into the logical loop. Let's pressure test the two possible answers. Scenario A. Let's assume that set R does contain itself.
Okay, if set R contains itself, it essentially walks up to the bouncer of its own club, but the bouncer's only rule is that you cannot enter if you contain yourself. Because set R contains itself, it violates the one singular rule of its own existence. So the bouncer has to kick set R out.
Correct. If it contains itself, the rules dictate it must be expelled, which inevitably forces us into scenario B.
Which is?
Set R is now kicked out of the club. It is sitting on the sidewalk. Because it is no longer inside the club, it is now officially a set that does not contain itself.
But wait, if it is a set that does not contain itself, it now perfectly meets the criteria for entry.
Exactly.
Set R was specifically defined as the collection of all sets that do not contain themselves. So, by definition, the bouncer must allow it back inside the club.
And the absolute microsecond it goes back inside.
It becomes a set that contains itself again, and the bouncer has to kick it out.
The moment it goes in, it has to be kicked out. The moment it gets kicked out, it has to be pulled back in.
It is an infinite, inescapable, high-speed loop of pure mathematical contradiction.
This raises an important question. Why does this matter?
To someone not entrenched in formal logic, this might just seem like a semantic parlor trick.
A mathematical definition that got a little tangled up in its own shoelaces. But we have to understand the existential stakes for the field of mathematics here.
Math is supposed to be the bedrock of pure, unadulterated truth. It is the language we use to calculate the structural integrity of suspension bridges,
To map the trajectories of probes sent to Jupiter.
to understand the fundamental laws of thermodynamics. You cannot have the foundation of universal logic contradicting itself at its core.
Precisely. If A can equal not A, then formal logic ceases to function.
If you can prove that math fundamentally contradicts itself, the whole epistemological house of cards comes tumbling down.
A very famous parallel to help understand why self-reference destroys formal logic is the classic liar's paradox in language.
The phrase, "this statement is false."
Yes. Let's unpack the liar's paradox deeply because it really gets to the heart of why self-reference is so toxic to formal systems. Let's assume this statement is false, is telling the truth.
Okay, if the statement is true, then what it is saying must be a fact. And what it is saying is that it is false.
So a true statement is declaring its own falsehood.
That is a direct contradiction.
So we have to assume the opposite. Let's assume the statement is lying. Let's assume it is false,
If the statement is false, then its claim that it is false is a lie.
which means it must actually be true.
Again, a complete logical inversion. You are trapped in an oscillating wave of true and false.
But while the liar's paradox is a fun trick of the English language,
And we accept that human language is flawed and ambiguous.
Russell's paradox proved that this same fatal flaw existed in the absolute, rigorous, mathematical definition of categorization itself.
The very way we group the universe into distinct logical boxes was proven to be fundamentally broken at the highest level of abstraction.
And this is exactly where traditional mathematicians panicked. They saw this infinite loop as a catastrophic bug in the operating system of reality.
A virus that needed an immediate emergency patch.
But the author of our source text takes an entirely different, incredibly bold path.
They view this infinite loop not as a paradox to be fixed, but as a profound philosophical revelation about the hidden architecture of reality.
Exactly.
So what does this all mean? How does the author resolve a mathematical collapse that terrified the greatest minds of the 20th century?
They don't do it with more math. They do it with a radical shift in perspective. And this introduces us to the concept of the one and the ultimate superset.
To resolve this, the author asks us to step back. Look away from set R the VIP club for a moment, and look at the absolute ultimate superset, the set of all sets.
X such that X is a set.
The largest conceptual container possible, encompassing everything.
The author points out that this ultimate superset can technically be broken down into two distinct halves.
The source text states that the set of all sets equals the set of all singleton sets, unioned with the set of all non-singleton sets.
And we should clarify the term unioned here, as it's a specific set theory operation.
By unioned, the text simply means combined together into one comprehensive pool.
You take everything that lives entirely alone in its own category, you take everything that exists in a group or a relation, you pour them both into one infinite bucket.
And that bucket contains absolutely everything.
Building on this absolute totality, the author introduces a conceptual entity they call the One.
The One represents everything, the entire universe, all of existence.
Every atom, every thought, every physical object.
Every abstract concept, space, time, and logic itself. It is the absolute most expansive conceptual container that can possibly be conceived.
The One encompasses all of reality. There's nothing outside of it. And the author argues that the One exists in two distinct fundamental modes.
Mode number one is what they call the unmanifested mode.
And this correlates perfectly to the mathematical concept of the singleton set we just discussed.
Let's really break down this unmanifested mode. In this state, the One is a true, unbroken conceptual singularity.
Think about the implications of that. If the One is literally everything in existence, then by definition, there is absolutely nothing outside of it.
That is the critical leap. There is no external perspective.
There is no separate entity to look at it, witness it, measure it, or draw a conceptual boundary around it.
Wait, I need to push back on that because someone like Cantor or Russell would probably hate this.
They probably would.
If there is no boundary, how can it be a set at all? Doesn't the very definition of Cantor's set, definite, distinct objects of our thought, require a boundary to distinguish what is inside the set from what is outside?
That's a great point.
If everything merges into a singularity, haven't we just stopped doing math entirely?
That's exactly the tension the author is highlighting.
Yeah.
You have to stop doing traditional boundary-based math at that absolute highest level of infinity.
Because in this highly specific, unmanifested state, the foundational mathematical equation we discussed earlier actually mutates.
Earlier we said Earth in brackets does not equal Earth. The conceptual container is never the physical contents.
But for the One in the unmanifested state, the container of the One does equal the One.
That is a staggering philosophical leap. You're saying the container and the contents become utterly indistinguishable.
Because the very concept of a container requires a boundary, and a boundary inherently requires an inside and an outside.
When there is literally no outside, because the whole encompasses all of reality, the container and the contained collapse into a single, indivisible reality.
It is a singleton set in the absolute purest sense. The boundary dissolves because there is no empty space for the boundary to occupy.
So in the unmanifested mode, the paradox cannot exist.
Because the paradox relies on a set entering or exiting a container.
If there's no inside or outside, there's no movement. There's no bouncer. There's no club.
But here's where it gets really interesting. Mode number two, the manifested mode.
Because obviously when I look around my room right now, I don't see a featureless singularity.
We live in a universe filled with distinctly separate things. Planets, people, podcasts, coffee cups, atoms.
Exactly. In the manifested mode, the One acts as money. It takes form.
It divides itself into the multiplicity of the universe we experience.
And crucially, because it has taken the form of billions of different distinct objects and consciousnesses, it gains the ability to witness itself.
I can sit here and look at you. You can look at me.
The universe is actively looking at the universe from countless different separated perspectives.
So because it acts as many, because it creates these internal divisions and perspectives, it becomes a non-singleton set.
It's a massive container holding billions of distinct, observable things.
If we connect this to the bigger picture and pull it all the way back to Russell's paradox.
The paradox only exists because formal mathematics assumes there is a hard, absolute binary boundary between the container and the things inside the container.
It relies entirely on the strict separation of categories.
Right. It relies on the bouncer being distinct from the club and the club being distinct from the people on the sidewalk.
If they aren't strictly separated, the logic loop doesn't trigger.
But the author proposes a radical alternative. At the absolute highest level of existence, when dealing with the totality of everything, that boundary is not fixed.
It is an illusion created by perspective.
The boundary becomes completely fluid depending on the mode of observation.
Oh, I see the architecture of the argument now. When you look at the universe as a collection of separate, manifested things, when you insist on drawing rigid boundaries between objects, you inevitably get caught in Russell's paradox.
The boxes try to hold themselves, the self-reference spirals out of control, and the logic breaks.
But when you look at it from the unmanifested perspective, the boxes and the things inside them are made of the exact same continuous substance.
The paradox is just existence trying to look at itself in the mirror and getting confused by the reflection.
It is a profound conceptual shift.
It suggests that the logical contradiction of Russell's paradox isn't a failure of human intelligence at all.
It is actually a mathematical pointer.
It's mathematics' own internal alarm system telling us, hey, your rigid binary categories of inside and outside fundamentally break down at the scale of infinity.
At the ultimate level of reality, the container is the contents. To make this dual-mode concept concrete, because I know we're floating in some very deep philosophical waters right now,
We definitely are.
the author provides an incredible, highly visual analogy in the text. I want you listening to really visualize this with me because it brings all the math into sharp focus.
Imagine an infinite two-dimensional black plane. It has no edges, it has no borders, it has no top or bottom.
It just stretches infinitely in all directions. It is pure, unbroken, endless blackness.
This represents the unmanifested state.
But this infinite black void is creative. Suddenly, parts of the void decide to pinch together.
The fabric of the plane folds and shrinks down to form distinct geometric shapes.
Imagine a section of the infinite blackness shrinking into a tight white square. Another section pinches and twists into a white circle, another into a triangle.
Now we have a plane with distinct observable shapes resting upon it. We've entered the manifested state.
The author then provides a categorization table to classify what these shapes are and what they are not.
This is essentially an exercise in set theory, but done visually.
Let's walk through the author's table, because the logic here builds beautifully. If you point your finger at the square and ask the positive question, what is a square?
The answer is simple and obvious. The answer is the square shape.
But if you flip the inquiry and ask the complementary negative question, what is not a square, the answer gets much more expansive.
What is not a square? Well, the circles are obviously not squares. The triangles are not squares. The pentagons are not squares.
And the infinite black plane itself is not a square.
Right. The background void is definitely not a square. It's the empty space between the shapes.
So far, this makes total logical sense. It perfectly mirrors how we normally categorize the physical world. A coffee cup is not a table, and neither of them are the room they sit in.
But then, the author hones in on the very bottom row of this categorization table, and this is where the massive aha moment happens.
The bottom row shifts from the shapes and asks, is a plane versus is not a plane?
Let's analyze this bottom row through the two distinct perspectives we just unpacked, the unmanifested and the manifested.
Perspective number one, the unmanifested view.
If you ask the question, what is not a plane? From this totalizing perspective, what is the answer? The answer is nothing. There's absolutely nothing that is not a plane.
Let me make sure I'm translating that correctly. You're saying that because literally everything, the squares, the circles, the triangles, they're all just pinched, shrunk pieces of the plane itself.
They aren't foreign objects placed onto the void.
They are made of the void's own fabric. The shapes are the plane. The void is the plane. There is no outside material. It is all one continuous substance.
Exactly. From the unmanifested perspective, the shapes are just the plane playing an infinite game of form and geometry.
The boundary of the square is an illusion. It's just the plane folded in on itself.
But let's look at perspective number two, the manifested view. The view where we strictly enforce boundaries and see distinct, separate objects.
If you ask what is not a plane from this separated view,
The answer is the shapes.
the square is a square. It has edges. It has corners. Therefore, it is not the infinite, edgeless background plane. The circle is a circle.
In this strictly categorized view, the plane is rigidly defined exclusively as the unshrunk black background space between the shapes.
What's fascinating here is how perfectly, how elegantly this visual analogy mirrors the one and resolves our mathematical paradox.
When you view reality as a collection of separate, defined objects with hard boundaries, when you choose to only see the shapes, you're operating in the manifested mode.
And in that mode, if you try to build an ultimate mathematical container of all containers, the logic inevitably collides with itself, and you end up with Russell's paradox.
The logic of separation defeats itself when pushed to infinity.
Because the square, by its very definition of having borders, can never contain the infinite borderless plane.
The limited shape cannot encompass the infinite background it rests upon.
Precisely. The moment you try to force the infinite plane inside the finite square, the mathematics breaks.
But when you shift your perspective and realize that the objects are the container, that the discrete shapes are literally made of the exact same continuous fabric as the infinite black plane.
You enter the unmanifested mode.
And in that realization, the paradox doesn't just get solved. It dissolves entirely.
There is no mathematical contradiction between the container and the contained because they are fundamentally, undeniably oneness.
That is just, it's a staggering way to reframe the problem.
It really is. It's a beautiful, elegant, deeply philosophical way to resolve the paradox that broke math. It turns a fatal glitch into a profound feature of reality.
It essentially argues that the paradox is the doorway, forcing us to understand that everything is intrinsically connected.
But as much as I love this, I have to play the skeptic for a minute. I have a very practical question for you.
I welcome the skepticism. Go ahead.
This is a gorgeous philosophical and metaphysical resolution, but let's go back to the early 1900s. When actual real-world mathematicians, people like David Hilbert and Gottlob Frege, were sweating over Russell's paradox, they weren't trying to achieve spiritual oneness with the universe.
No, they certainly were not.
They were just trying to get their formal logic to work. They needed math to be functional so we could build bridges, design electrical grids, and understand physics.
True.
So how did the rigid institutions of mathematics actually solve this in the real world without resorting to the metaphysics of the infinite black plane?
That is an excellent grounding question. And it is vital we look at the historical reality of this, because you're absolutely right. The mathematical establishment did not embrace the philosophy of the one.
They didn't dissolve the boundaries of the universe.
They took a much more pragmatic, rigid, and ultimately defensive approach. They essentially looked at the paradox and decided to put up legal guardrails.
Let's contrast our author's philosophical resolution with what you'd actually find in a university-level advanced math textbook today.
The most common, widely accepted foundation for formal mathematics today is called Zermelo-Fraenkel's set theory.
Often just abbreviated as ZF, right?
Exactly. When the mathematicians Ernst Zermelo and Abraham Fraenkel looked at the smoking crater of Russell's paradox, they didn't look for underlying metaphysical oneness.
They looked for a way to explicitly outlaw the problem from ever occurring again.
Wait, I want to make sure I understand that. They didn't solve the logic loop. They just made it illegal to create the loop in the first place.
Essentially, yes. That is exactly what they did.
In ZF set theory, they created a very strict, highly regulated set of axioms.
Axioms are the fundamental ground-level rules of a logical system that you simply cannot break.
And they designed these specific axioms purposefully to make it mathematically impossible to build a set that is too large or too self-referential.
So going back to our analogy of set R, the VIP club, of all sets that don't contain themselves, Zermelo and Fraenkel just stepped in as the city zoning commission and said, you don't have the proper permits to build a club that big. It's an illegal structure.
That is a brilliant way to frame it. Before Russell's paradox, mathematicians operated under naive set theory, which basically said you could form a set out of literally any distinct property you could think of.
Zermelo and Fraenkel killed naive set theory.
The axioms of ZF state that you cannot just arbitrarily define a set by any wild property you want, like all sets that do not contain themselves.
You are forced to build sets from pre-existing, well-defined sets using very specific, heavily limited operations.
They literally outlawed the mathematical syntax that creates the paradox. They ruled set R out of existence.
I have to admit, that feels a little intellectually unsatisfying. It feels like cheating. We can't actually solve the paradox. Our logic is broken, so we're just going to make it illegal to ask the question that breaks the logic.
It was a pragmatic fix.
What about Bertrand Russell himself? He's the one who discovered the ticking time bomb. How did he personally try to defuse it?
Russell was deeply troubled by his own discovery, and he spent years trying to formulate a fix. He took a different approach than ZF, developing a highly complex system, which he called type theory.
Type theory.
Type theory argues that the universe of mathematics isn't a flat, egalitarian plane where any set can interact with any other set. Instead, he argued that sets and their elements exist on strictly different, segregated hierarchical levels, which he called types.
Okay, walk me through the mechanics of that. How does a strict hierarchy fix the VIP club loop where it keeps kicking itself out and pulling itself back in?
Well, in type theory, you have basic foundational elements at type 0, then you have sets of those elements at type 1, Then you have sets of those sets of type 2, and so on, building upwards infinitely.
The golden, unbreakable rule of type theory is that a set of type 2 can only contain items of type 1. A set of type 3 can only contain items of type 2.
Oh, I see the mechanism. So a set can never, ever, under any circumstances, reach across the hierarchy and contain itself.
Because to contain itself, it would have to swallow an item of its own type, which violates the hierarchy.
It is permanently separated from itself by its type classification.
Exactly. Russell solved his own paradox by enforcing aggressive systemic segregation.
He built impenetrable hierarchical walls to ensure that the container and the contained were permanently separated by different stratospheres of mathematical existence.
I really want to highlight the incredible stark contrast here for you listening, because it says so much about how human beings process reality.
Think about how these two vastly different worlds approached the exact same collapse of logic.
The mathematical institutions, Zermelo, Frankel, Russell, they solved the paradox by building stricter walls.
They created rigid laws, artificial limitations, and complex hierarchical types to force concepts to stay separated. They forced the math to behave by putting it in a cage.
It was an act of containment, while the author of our source material, looking at the exact same paradox, went in the exact opposite direction.
They solved it by arguing that we need to tear down the walls completely.
They posited that the paradox only exists in the first place because we stubbornly insist on those artificial boundaries.
They argue that at the absolute highest level of reality, the container and the contained, the geometric shape and the infinite plane, the perceiver and the perceived, are the exact same unified entity.
It's the profound difference between managing the symptoms of a paradox by putting reality in a straitjacket versus curing the paradox by realizing the straitjacket was a hallucination the whole time.
It is a fundamental divergence in worldviews. One methodology seeks to control and dominate reality through endless, rigorous categorization. The other seeks to understand and integrate reality by transcending categorization entirely.
Which brings us to a moment to really digest everything we've unpacked today, because we have covered a massive amount of conceptual ground.
We certainly have.
We started this deep dive by learning how Cantor and early mathematicians attempted to put the infinite abstract universe of concepts into invisible logical boxes called sets.
We walked right into the mind-bending, system-destroying trap of Russell's paradox, watching what happens when those boxes try to hold themselves and the formal logic of our universe seemingly shatters into an infinite loop.
And finally, we explored a profound philosophical and metaphysical escape route from that shattered logic. The infinite two-dimensional plane, where the strict boundaries we draw and the distinct objects inside those boundaries are ultimately revealed to be made of the exact same continuous, unmanifested fabric of existence.
We took a mathematical glitch, a bug in the operating system of formal logic, and used it as a telescope to catch a glimpse of the one.
If we connect this to the bigger picture and bring this abstract math back down to your actual life, I want you to think about how often we operate exactly like Zermelo-Frankel set theory or Russell's type theory in our own daily routines.
Think about how much mental and emotional energy you spend trying to strictly categorize your world, your relationships, your skills, or even your own complex identity into neat, rigid, highly separated little boxes.
We do it constantly. I am a type 1 employee. This is a type 2 hobby. This is my work persona box. This is my family persona box. I am an introvert box. You are an extrovert box.
We build all these massive, exhausting hierarchical walls to try and make the chaos of our lives make logical sense.
But this mathematical journey we've just taken through set theory reminds us of a fundamental truth. Eventually, if you push those rigid categories hard enough, if you demand too much purity from your conceptual boxes, they break down.
They create paradoxes in your own life. The reality of who we are and how we fundamentally relate to the world around us is infinitely more interconnected, fluid, and unified than any rigid set of categories could ever hope to capture.
Which leaves me with one final provocative thought for you to mull over as you go about the rest of your day.
If every category, every label, or every rigid set we use to define our world and ourselves is ultimately just a shrunk shape, a temporary limited manifestation on the infinite black plane of existence.
What happens when we voluntarily stop identifying with the specific constrained shape we've been squeezed into?
What happens when you shift your perspective, dissolve the boundary, and start identifying with the infinite plane itself?
Are you just the conceptual container? Are you just the messy contents? Or are you both, simultaneously, forever?
This question well worth exploring on your own.
Thank you so much for joining us on this deep dive. Your brain has definitely earned a rest after that mathematical marathon. We will catch you next time.